Welcome everyone to the Foundry by Forge College. I am so excited to be your host for today's explainer. You know, as part of our Ethereum Dev Stacks and Frameworks track, specifically inside Hardhat Fundamentals, we are really rolling up our sleeves today. We're diving into the absolute art of drafting robust testing blueprints for your smart contracts using Mocha and Chai. Because, let's be honest, if you want to sleep soundly at night knowing your code isn't going to spontaneously combust on the blockchain, you are in the exact right place. So let's just dive right into this.
Okay, so here's the master schematic for our time together today. 1. Context, C-level to Ethereum. 2. Mocha, your testing blueprint. 3. Lifecycle hooks, clean slates. 4. Cha, firm assertions. 5. Building the suite. And finally 6. The inspection report. Let's get moving.
Section 1. Context, C-level to Ethereum.
Before we lay down our new tools, I kind of want to validate the mental whiplash you might be feeling right about now. In our previous lesson, we were deep in the weeds of Solana's C-level CPU management, right? Totally different world. And now, we're suddenly jumping over to our Ethereum testing stack using Hardhat. Moving from parallel processing resource management straight into writing JavaScript testing frameworks for EVM chains, yeah, that's a pivot. But your local Hardhat environment is running, the local node is spinning, and now we need to actually write the tests to prove your Ethereum contracts work.
Section 2. Mocha, your testing blueprint.
So Mocha is a JavaScript testing framework, but honestly, I want you to think of it more like an architect's blueprint. It provides structure using two main tools, describe blocks and it blocks. Think of a describe block as drawing zoning lines on a property. It groups related features together so we know exactly what area of the contract we're looking at. Inside those zones, we have our it blocks. These are your individual stress tests. They're the highly specific scenarios we're going to run our product through. Simply put, describe organizes and it executes.
Section 3. Lifecycle hooks, clean slates.
Now, when we run dozens of these stress tests, we absolutely cannot have the results of test number 1 contaminating test number 2. We need a perfectly clean workbench every single time, and that's where Mocha's lifecycle hooks come in. Before runs just once, which is great for a one-time really expensive setup. Then we have after each for cleanup. But the absolute crucial one here is that middle row, before each. Think of this as your vital factory reset button. We use beforeEach to deploy a fresh, brand new instance of our smart contract right before every single it block. It guarantees an isolated state, meaning our tests are completely independent of one another.
Section 4. Chai, making firm assertions.
So we have our blueprint and our clean workbench, but now we need an inspector. Enter Chai. Chai is the rigorous quality assurance inspector to Mocha's blueprint. It's an assertion library that uses this wonderfully readable expect syntax. This is the exact moment where we stop politely asking our code what it's doing, and we start making firm, unyielding demands of its behavior. We literally say, I expect this retrieve value to equal exactly 42. If it doesn't, Chai throws an orange warning flag, fails the test, and stops the whole assembly line. Basically, Mocha organizes the test, and Chai decides if it actually passes.
Section 5. Building the test suite.
All right, we've got Mocha zoning things out, beforeEach resetting our state, and Chai enforcing the rules. Let's see how this assembly line actually comes together in Hardhat. Here are the mechanical steps. Step 1, setup, using describe to define what we're testing. Step 2, deploy, using beforeEach to give us that fresh contract instance. And step 3, assert, using our it block alongside Chai's expect statement. It's a 1-2-3 punch that you're going to use hundreds of times in your Web3 career.
Let's look at how this applies to a theoretical simple storage contract. Imagine a contract that just writes a value and reads it back. First, we set up our describe block, naming it simple storage. Inside, our beforeEach hook tells Hardhat's ethers.js library to deploy a brand new simple storage contract. Then, we drop into our first it block to check the default state. We call the retrieve function, and we use Chai to expect that value to equal 0. Next it block, bam, the beforeEach fires again, wiping the slate completely clean. We then call the store function to save the number 42, call retrieve, and expect the result to equal 42. It's incredibly logical and honestly immensely satisfying when it clicks.
But of course, this is blockchain engineering we're talking about. So eventually, you're going to stare at your monitor and scream this exact deeply frustrating question. Why did my math fail? You will write a test where you literally expect 0 to equal 0, and Chai will just confidently tell you that it failed. No way, right? Well, this brings us to the infamous big number trap. You see, Solidity uses massive numeric types, like uint256. Standard JavaScript simply cannot handle numbers that large safely. So, ethers.js wraps these values in a custom object called a big number. The trap here is that a big number representing 0 is an object, not a JavaScript number. When you tell Chai to expect a big number object to equal a standard numeric 0, it panics. The fix? It's so easy. Just append .toNumber to your retrieved value before you run your Chai assertion, or compare it directly against another big number. Seriously, write this down. It's going to save you hours of debugging.
Section 6. Running and debugging tests.
All right, the blueprint is drawn, the assertions are set. It's time to run the machinery and look at the final inspection report. You'll pull up your terminal and punch in this exact command, npx hardhat test. Under the hood, Hardhat instantly spins up a local invisible blockchain node, deploys your contracts, runs your Mocha tests, evaluates your Chai assertions, and hopefully, if you follow the schematic, prints out a beautiful column of satisfying dark green check marks.
But look, when the orange failed marks inevitably show up on the inspection report, don't panic. Just follow this debugging checklist. First, check for syntax errors. A single missing bracket will crash the whole thing. Second, contract not found. Make sure your Solidity file actually compiled successfully. Third, assertion mismatches. That's usually our old friend the big number catching you off guard. And finally, the trickiest, most dangerous one, async mistakes.
This is absolutely crucial. Always await your async contract interactions. Interacting with a blockchain takes time, right? It's an asynchronous operation. If you forget to write the word await before calling your contract store function, JavaScript will just blow right past it and run your assertion before the transaction ever finishes. And the scariest part, sometimes forgetting await makes a broken test accidentally pass, which renders your entire safety blueprint totally useless. So always await your promises.
Let's wrap up with a little guiding philosophy. Isolate setups so tests are independent, name tests clearly, and prefer small, single assertion it blocks. If you really internalize these principles, adding more features to your smart contracts becomes far less risky. You're building a safety net that catches regressions instantly. And you know, these are the exact professional engineering habits that scale perfectly as you move through broader educational programs, like the ones we offer here at Forge College. It's all about building absolute trust in your code.
And that sets the stage perfectly for where we go next. Once you have this foundational blueprint mastered, our next explainer is going to dive deep into asynchronous testing patterns, handling complex promises, testing emitted events, and asserting transaction reverts. But until then, I want you to ask yourself, if a single missing await statement can give you a false sense of security, what other silent vulnerabilities are hiding in untested code? I really encourage you to keep exploring and expanding your Web3 toolkit by visiting forge.college to learn more about this subject and discover the other amazing courses we have available. Thank you so much for joining me on this explainer. Keep writing those passing tests, and I'll see you in the next one.